buffers with our pKa's. So information that we pulled from this, if I can attempt to quickly summarize the stuff that we already had. We decided that this compound was an acid, and we decided that because for a couple reasons. One, it starts with a low pH, and two, we're adding a base. Right? Well, if the pH is going to change, and we started with a base and adding a base, the pH isn't going to change. Right? We saw two rises, which we decided was ultimately because we had two acidic hydrogens. So we're looking at H2A as our starting compound. The reason the pH rises is that we lost a hydrogen off of it. Okay, that hydrogen was effectively reacted with the hydroxide, so we see that jump in the pH. So at that point, we would then have HA, and then I don't know how nitpicky I'll get on this, but you will for sure see this on an exam. And I would expect that you will also give me that minus when you write out HA. Why should you specify that minus? Because that's actually what the structure is. It is negatively charged. So it makes sense to put that there. The next spike is spiking because, again, we've lost another hydrogen. What we'd have at that point would be A minus 2. Okay. I don't like numbers.
And what were the application points again? I'm sorry.
We'll come back to that in just a second here. The other way that we could format this is instead of looking at it as a standard titration curve, we could convert it into a chemical reaction. So we're taking H2A, which ends up being in equilibrium with HA minus, in equilibrium with RA minus 2. Okay? And of course, to shift to there, we're adding or removing hydrogens. Okay? And what we're concerned about in these cases is in that middle range, what do we have? What's special about that range? That's not the range, but you've got the right idea where we'll go next. What's special about those ranges? That full range. What happens to the pH? pH stays relatively constant. So what we've got in those now purple ranges are buffers. Okay. So to be a buffer, we have to be somewhere in that flat range. Okay. Let's go ahead and test you real quickly on this. Let's take a look at that orange dot. Okay. What happens at that orange position? If I was somehow able to build a solution that put me at concentrations of H2A and HA minus that got me to that point, is that point going to be a good buffer? Why not? Okay. As we add base, what happens? pH drastically changes. I'm not buffering the pH. Go ahead.
So is buffer considered a zone?
It's ultimately the range, and we'll talk about kind of the limits on that range here in a section, in a minute here. But yeah, it's a range where the pH stays stable both directions. Okay. If we take a look at our orange point, when we add base, okay, our pH drastically changes. So by definition, it can't buffer base. But what happens if we add acid? Okay, it goes back, but how much does it go back? Not by much. So it does buffer acid fairly well. It just doesn't buffer the base. When we're thinking about buffers, it's supposed to go both directions. Okay, you have to be able to balance out both an acid addition and a base addition. So that orange spot, while it may do a really good job at buffering the addition of an acid, it does a horrible job buffering the base. Okay? So that orange spot doesn't classify as a good relative mixture for a buffer. Okay, so really what we want for our buffer is to have something within that purple range. Okay, can we quantify it a little bit? So this would go back to Scott's, I think you were saying earlier, what about the very center of that purple range? I think you were telling me something important about that point. Okay, if we look at our very center of each of those, 1, 2, 3, 4, 5, okay, of each of those buffer ranges, what's true at that point? Don't tell me the pKa pH thing yet. What's the thing that gets you to that?
Concentration equals.
Okay. In this first one, we're shifting from H2A to HA. Exactly halfway there means what about the concentrations of H2A relative to HA? They're equal. So at that blue point, our concentration of H2A equals our, and we'll call this point 1, equals HA minus. And this is our point 1. If we look at our point 2, what happens there? Concentration of HA minus will equal our A minus 2. Okay. If those cases are true, what happens to our equation? Now it doesn't matter what concentration I have of one of these. The other one's exactly the same. So if we picked 1,000, we'd get 1,000 over 1,000. It goes to log of 1. What is the log of 1? 0. So the big conclusion that comes from our titration curve is at that point, we can determine graphically that the pH equals our pKa. Okay. So if we take a look at point number 1, what's roughly our pKa?
2.
We're looking at a pKa of about 2. If we take a look at our second point, what's our pKa? Sorry, I'm in the wrong section of my graph. 2, 3, 4, 5, 6. Yeah, it looks like about 6. Okay. And we can start to draw some conclusions then about that information. Okay. What functional group is going to get you a pKa so low? It's a trickier question, particularly if you haven't memorized your pKa's. It's going to become more important when we move into chapter 3. The chapter 3 is looking at carboxylic or amino acids, pKa of about 2. You're actually starting to push into your carboxylic acid functional group. Okay. Not exactly. Your standard carboxylic acid is at 4. Why would amino acids drop down to 2 from 4? When we look at an amino acid, one bond away, there's a nitrogen. What's special about the nitrogen? It's electronegative. Why does the pKa drop? We have an inductive withdrawing effect causing our acid to become more acidic. Okay. So the idea is to be able to look at the curve and label important pieces of information off of that to be able to draw some kinds of conclusions. Questions about any of that?
So because it's withdrawing, is that just making it easier for it to be deprotonated?
Deprotonate that, yeah. Which is why your pKa becomes more acidic. You get a lower pKa. Yeah. All right. Any other questions on that? Probably drop a whole bunch of numbers and things into that, but we won't worry so much about that. So really what I expect you to be able to do is to label and interpret your titration curve. Okay? So lots of interpretation came off of this. Identifying what species you started with. Was it an acid? Was it a base? Okay? If it's an acid, is it a polyprotic acid? How do you know it's polyprotic?
Because of the multiple points.
We get multiple points of inflection. Okay? How do we know that's a point of inflection? Where's this curve aiming? Here, I might make everybody unhappy with me, but I'm going to erase everything. Can I do that? Okay.
So if that graph was like inverted and you started with a base and there was 2 inflection points, does that mean you had 2 OHs?
You had 2 basic positions.
Right.
So be careful about calling
Okay.
it an OH, because it may not be OH.
Okay.
If we take a look at that section of the curve, what happens? Our curve is ultimately aimed upwards. If we look at the next section of the curve, where is it aimed? Okay, it's concave downwards. What we're looking at our equivalence point is a point of inflection within our graph. Okay, so you might hear that reference show up as well. Okay? Questions about that? Okay. So kind of in the lab, which is going to be more relevant, particularly for those of you that are in the lab, how would we go through and select a buffer? What are we going to work with? Okay, so what we're going to have is a ton of different possible buffers that we could go through and use. We have to make sure that we pick the right buffer. Okay, so one of our considerations is what pH do we want? So if we have a buffer that maintains the pH at 2, but we're trying to represent something that happens in the body, probably not the best buffer to use, because in the body we're looking closer to a pH of 7. Okay, so it doesn't make sense to use a buffer that centers around that range. So when we look at all of our buffers, ultimately what we'll be given is a pKa. We're not told a pH or anything else. So if we want a target pH, how do we know which buffer to use? Where is our buffer best functioning? Okay, we went back to our titration curve. Okay, at our half equivalence point, okay, so let's pick the one that's a little bit higher up, just because that's where I'm looking at it on my screen. We're looking in this range. Okay, where's the absolute perfect position to buffer? Right at 6. Why 6? It's exactly in the middle. I can go add acid or base, and I don't have any kind of drop off on either end of it. Okay, it should stay relatively constant. What was special about that point? The pH and the pKa were equal to each other. So if I want to find a buffer that's going to balance my pH as best as possible, what should the comparison be between the pKa and the pH? They should be the same. So if we go back to trying to achieve these individual pHs, what we'd go back and do is see which of our buffers happens to have a pKa that is closest to that. All right? So if we were going to try and get a pH of 1, what buffer would we use? Probably use phosphoric acid. Okay? Is it perfect? No, but it's as close as we can get with the buffers we've got. All right? How about a pH of 4?
Carbonic.
Okay, why carbonic acid? I picked that pH intentionally. Okay. What's the interesting point about pH 4? That falls pretty much halfway between our phosphoric and our carbonic. Okay. So potentially either of those are possible. Okay, at least with what we've got here.
You couldn't mix them.
Okay. We could take it to the next level and really start to mix our buffer systems. The problem with mixing buffer systems is now you have two different things and you'd have all sorts of other things to go through and balance. Okay? So that is possible. It's generally not a good idea because it's not just going to average out. You're going to get one dominating over the other and you'll get kind of a weird interplay with your solution. Makes it more difficult to predict what's happening. Yeah?
You only have like a 1.8 difference and a 2.4 difference. Does that make sense?
So we would want to target the one that's closest. I didn't actually look at the numbers to see the difference. I just guessed. All right. What about 6? Probably the carbonic acid. 7. Okay. I did a better job counting this one. C or D, 7 hits it right in the middle. Okay, and pH of 8. Probably again tris, but we could probably drop in E as well. Okay. If I want it to be exactly at any one of those pHs, none of these buffers are going to work. So how can I get the pH to be exactly what I want? Titrate with what? So let's take a look at A. Our very first case. If I want a pH of 1, okay, if I just put in my phosphoric acid, we might expect a pH in my perfect buffer range, so where I get equal concentrations of those, right about 2. How can I guarantee I get to a pH of 1? Okay, remember, in all of these cases, what we're looking at is HA in equilibrium with A minus. And we picked our buffer to get us to exactly match that. So we're looking at equal concentrations of HA and A minus to get us to a pH of 2.5. I want a pH of 1. How can I get it to a pH of 1?
More acid.
add acid. Okay? So we can titrate in a little bit of acid. How do you know you've added enough acid? Litmus paper won't be accurate enough to get it exactly to 1, but you've got the right idea. Okay. Phenolphthalein is an indicator, which is ultimately another buffer system, also not going to be accurate enough. The instrument that sticks it in there, known as the acidometer, is nice. I like that one. We might change that. Work on converting the name across. We're looking at a pH meter to do that conversion. Okay. How else could you do it? Come on, 152.
Titrate with base to see if.
No, not even any titrations. Nope, you're still thinking experimental. You're thinking the easiest answer to go through and do it, which I admire you for. Okay? But how, before you even go into the lab, can you decide how much acid you're going to have to put into that? You can calculate it, going through your ice charts, determining the concentration of the acid you're adding, how much of that acid do you need to add to cause a shift in the concentrations to adjust to our pH. Okay? Pretty awful. Okay? And I will fully admit that I doubt any biochemist goes through any of those calculations. Okay? They probably go into the lab, start adding acid. Nope, it's not the right pH. Keep adding acid. Oh, there it is. Mind if I overshot it, so they add a little bit of base. Okay? Okay? They aren't going to go through and run the calculations.
You have a pH less than 1? Or
Yeah.
lower than 1?
Yeah, you can get pHs into the
Point some.
well, you can get them very low. Technically, to get much lower, you have to shift out of water. Water-based systems have a problem getting pHs extremely low, and that's because water is the limitation. Prevents the dissociation of hydrogen ions. So when you look at pKa's, typically we would look at things greater than 0. Okay? But do we have pKa's less than 0?
Sure.
Yeah, like all of your strong acids are usually at a -6, -7 pKa. And those we define as strong acids, but you can get acids that push down into like the -12, -20 range, known as superacids. You can't function with those in water because it ends up just reacting so much and it converts across to something else. Okay, so in our lab situations, we would try and decide. So in the case A, okay, we would just add acid. And as far as determining the amount of acid added, we said we could calculate it, or we can just sit in the lab and slowly add it in there. Okay. Along the lines of sit in the lab and slowly add it in there, what should the concentration of that acid be that we're adding to it? High or low? Okay, because you're going to start titrating an acid into this. Okay, should I titrate in a concentrated acid or a weak acid?
Concentrated.
Okay. What happens if that difference in your pH, okay, think back to your titrations, you add a single drop to a solution that you thought was close to the end point and you overshot it. What happened? You added too much base. Okay, in those cases, you added too much base and you overshot your end point. And that's ultimately because too much base was added. How could you limit how much base was added? Try smaller drops or a diluted base solution.
But you're going to need a stronger acid.
We'll need a strong acid in dilute concentrations. Okay, so we definitely want to, when we're trying to do these titrations of getting it to the correct pH, we want to use the most dilute acid we can. It does, by definition, need to be strong because that encounters the other issue that Carlos was mentioning, that we end up within 2 buffers, okay, in the same solution. While it does work, it gets a little bit more complicated to work
It's
with.
going to be, it would need to be a pH less than 1, correct? Otherwise, you're just going to...
No, it has to do with the concentration of the acid. Okay, so you don't want to look too much at the pH. You want to look more at how much acid you're adding. Okay, so it's the amount of the acid, the moles of the acid. The volume isn't all that important. Okay. What happens if we jump to pH 7? Let's do pH 7. So let's erase all that again. If we just looked at our 2 options for 7, we said our 2 options were C and D, right? Right? If we use C, what do we have to add to get to our pH of 7? Okay, we'd end up adding our base. Okay. Again, we'd want to use a strong base in dilute concentration, okay, so that we can control the addition of that base a little bit better. What happens with D? I want to go through and again add acid. Okay, so we're trying to balance that out as quickly as we can and effectively. Yeah.
Could you just mix C and D together to get 7?
So that's what he was asking. That kind of works. The problem with that is that our buffer or biological systems tend to be very finicky about their pH and ultimately what buffers are used. So we need to be very careful in our buffer selection, and one buffer adds one variable. If we add another buffer, we have yet a second variable. There's too many different things to control. While it doesn't not work, it makes it more difficult to guarantee your results. Okay. So we can adjust with different buffer systems or doing multiple buffers. Most will stick with a single buffer. The more common ones I've heard are actually your HEPs and your tris. Okay. So in a situation where we could use two different buffers, C versus D for instance, how might we decide which one to use? Particularly in those cases, pH didn't really matter. Okay. We're going to get to that 7 pH either by adding acid or by adding base, and we're there. D. Why would I choose C or D? You would choose D. Why do you want to choose D?
Because it's easier to add more to get more acidic to 7 than it is to change the base from 6.8.
You're doing the exact same chemistry.
It's more simpler.
How is it simple?
It's only 2 compared to going through something.
So you could look at structure. You could say the structure looks crazy different. Okay. Let's pick an experiment. Let's monitor the synthesis of ATP, okay, from ADP. How do we make ATP from ADP? What do we need? Phosphate. If we're going to study that reaction, we're concerned about the concentrations of our reactants. Okay. What happens if we go through and use a phosphate buffer?
You're converting.
Some of it is getting used in our reaction, some of it is getting used in our buffer system. They could potentially be competing with each other, and we're not going to be able to interpret as easily. Okay? So you'll notice that a lot of buffer systems that typically get used, you'll see these weird acronyms for them. Okay? Pipes, HEPs, tris. And that's because those are unnatural buffers. They aren't used in a biological system, which means they aren't going to compete with any other reactions. Okay? So we don't have to worry about concentration shifts due to buffering or concentration shifts due to the reaction we're monitoring. We can run into issues with that, but that at least kind of separates those two variables. That the system we're using to monitor it doesn't affect the reaction that we're trying to monitor. Make sense? Yeah.
What does the P and the L signify?
Next to the letter.
Oh shoot, why did I specify that?
They're liquid and something else or not?
No.
Just guessing.
And why did I say P and L? I can tell you what the difference is. Hydrogen phosphate is a very common biological buffer system. Think about all the phosphates that you need to transfer ATP back and forth. So within a cell, most cells are buffered with hydrogen phosphate. Think back to your blood. Okay. What is your blood transporting typically? Oxygen to your muscles, but then what comes from your muscles? CO2. What is carbonic acid transporting? CO2. Okay. Your blood is typically balanced out by a carbonic acid pH system or a buffer. Cells are typically through a phosphate. I don't remember why I said P and L. I can't for the life of me think what that
So
means.
because of those, the ones with the P are more biological and the other ones won't interact as much?
But biological doesn't mean P. I don't get where the P came from. I don't know why. Maybe I threw it in there just to be different, so I didn't forget to talk about it, but didn't want to give away that that's what I was talking about.
You remember.
But ultimately, that is your big difference. Your carbonic acid and your hydrogen phosphate are both common biological buffers. Okay? The other ones here, your pipes, your HEPs, and your tris, are unnatural. No, unnatural isn't L. I don't know why I picked P and L. Did I make a note of it? No, I didn't make a note of it either. I do something down there? No, I didn't do something there. I have no idea why I said P and L. Why did I not put one with phosphoric acid?
Because it's so low that it's not even.
It's in such a low range that most cells aren't going to function at that level. We don't use phosphoric acid in its fully acidic state. We remove one of those hydrogens, and we deal with or I think actually two of those hydrogens to get up into that hydrogen phosphate range, which gets us into that pH of natural cells. Okay. So that's why I didn't specify anything on the phosphoric acid.
Where would gastric acid land?
I have no idea. Yeah. It's low. One thing that we could evaluate as well, which is going to come in play when we look back at our amino acids. What we're doing is trying to ultimately compare our pH and our pKa, which we could also get from our titration curve. If our pH is lower than our pKa, oh, I gotta go back one more. So if we say our pH is lower than our pKa, what species is primarily present? So if this is our pKa, and we say our pH is lower than that, come on, Mark. We're looking careful, what did you say? We're looking at our acidified buffer. If it's higher, we're looking at our basic buffer. What else can come into play with that? What charge would we expect on our buffer if our pH was lower than our pKa? What charge? Neutral. What happens if we're higher? Okay, we can see a charge appear. And it, again, depends on what system you're using to buffer. So we can't guarantee that. Okay? But if we've got an idea of what our reaction is, we can start to look at, okay, if the pH lower than that, okay, that means I'm looking at the acidic side of it. If the pH is higher than the pKa, then I know I'm looking at the basic side of it. Okay? Kind of makes sense? Okay. So, considerations for the buffer. What things do you think are going to be important? Okay, the system you're monitoring, what about that system that you're monitoring? You're right, there's at least two things I can think of with that one statement. We want to maintain the pH of where your system is. We want to get that same pH. What else? We just talked about this one.
You don't want it to compete.
We don't want it to compete with that reaction. Okay, so we want to kind of shift off of that. What other considerations? I actually forgot my big list. There's like 5 of them. Okay, so we want a suitable pKa. We'll just kind of go through it. Could look at solubility. That's a good point, actually. If the concentration of our buffer is really, really, really high, okay, water, as fantastic a solvent as it is, and when we looked at it in organic chemistry, we didn't look at the limitations of the solubility of water. But water does have a limitation. We can only put so much stuff into it before it says, I can't take anymore. So if we put a buffer system that has an extremely high concentration, will our proteins dissolve in it? Possibly, but also possibly not. So we need to make sure that the concentration that we pick of our buffer allows for the solubility of whatever we're trying to study. Okay? And if you don't believe that, okay, take a container of water, add some salt to it. What happens? Dissolves. Add more salt. Add more salt. Add more. You'll get to a point where eventually the salt stops dissolving. What you've done is then add more salt. You'll reach a point eventually where you've saturated all of the potential hydrogen bonding interactions that water can do, which means nothing else will dissolve in it. Okay? It's something that we use or take advantage of in organic chemistry as well. When we go through and wash solutions with a brine solution, that brine is saturated salt solution. So that does two things in organic chemistry. That pushes water out of our organic layer to try and dilute that brine, but it also pushes organics out of our aqueous layers and back into the organic. Okay? So we can manipulate that kind of osmosis effect. So good call on our concentrations. Hey, good, we got our first two. Let's see. Suitable ionic strength, so we looked at the extreme. There's the other option. What happens if we have very small amount of buffer present? Okay. Let's say I put in a buffer system where it's 1 molecule of HA and 1 molecule of A minus. If I add acid, pH stays constant. If I add 1 more molecule of acid, it's going to change the pH substantially. So not only do we want a concentration of our buffer to not be too high, but we don't want it to be too low, because if it's too low, then yes, it will buffer, but it can't buffer for long. Okay? So we're looking at the buffering capacity. Too high of a concentration, we have solubility issues. Too low, we lose our buffer ability very, very quickly. Okay? So there's our solubility issue. Cool, good job. And non-biological nature of the buffer, okay, which I think is kind of an odd one to mention, but your textbook definitely threw it in there. I think that kind of falls under number 2, no interference with your biological process. Okay? So most buffers tend to be non-biological because they won't interact at all with the process you're monitoring. Okay? Particularly if we make them oddly shaped structures, then they can't even interact weakly with our proteins. Okay? We make them kind of this odd glob. It's not a small enough molecule to make it into the protein, and it's oddly enough that it can't fit into any little crevice. Okay, so we're trying to make sure that we keep the protein as happy as possible without changing too much of its natural properties. Okay? Yeah, here we go. Organic question. I'll give you guys some time to think about this one. Of these 2 compounds, they are both common buffers. Okay? They will be used in buffer situations. Okay? However, one of these is used to buffer at very low pHs, and the other one's used at very high pHs. Which one's which? All right, yeah, I'll go ahead and pause that. Okay. We've got our nitrogen. We also have oxygens out here. In our second structure, we have oxygen, nitrogen, and the oxygen. And I circled 3, but that's an oxygen. All right. What about the SO3? Do you think that's going to contribute to the buffering system? Probably not for what we're targeting. Why? What's the pKa of that hydrogen out there? As a general hint for this, let's draw it out. There's SO3. What's the pKa of that species? You're looking at what compound? H2SO4, which is by definition strong acid. pKa of that functional group is wicked low. Okay? That functional group is not going to contribute to our buffering system because the pKa is way too low. That's not going to work for our biological buffering system. Okay? So that's going to be pretty much immediately lost. So what we're now evaluating, okay, in our first one, is just the nitrogen. There is no other choice. But how about in the one like the red circles? Which atom is going to be the one contributing to our buffering system?
Oxygen.
Okay. What is our atom going to have to do in either case? There's no aromaticity. There's no aromaticity because we don't have any pi bonds. We need a pi system to be aromatic.
Would it have to break a bond whenever it takes up a hydrogen?
I don't know about your first part, but I like your last part. What is our buffer doing in these cases? Our buffer needs to act as a hydrogen acceptor, the long version, or a base. Which atom is going to act as a base? Oxygen or nitrogen?
Nitrogen.
Nitrogen because? No. What's the difference between oxygen and nitrogen? Electronegativity. Which one's more electronegative? Oxygen. What does that mean it does with its electrons? It holds them. Nitrogen, being less electronegative, is much more willing to share those electrons with a hydrogen. What we're comparing is this nitrogen to that nitrogen. Yeah, I know, it's brutal. but it will come back and haunt you. And you notice, with all of these explanations, particularly for those of you that went through organic chemistry with me, we're always going back to electronegativity. Okay? Electronegativity is a powerful tool to help us predict what's happening within this. All right, so we are looking at the ability for each of those nitrogens to now accept a hydrogen. Right? So now that we've got where our buffer is occurring, now I'll leave you to figure it out again. Break it down again.
Like an acidic nitrogen, or?
And to make you feel better too, this one took me a long time to think through and process. So it's not a particularly easy question. I just want you to start thinking about these intermolecular forces and approach this. Okay? So let's erase those all again. That's going to be getting towards your answer. It has to do with substitutions. Okay? What we're concerned about, okay, with each of these nitrogens is them acting as what? A base. But how are we monitoring this? Which one has the
Concentration, the ability to.
concentration of hydrogen ions? So what we're looking at is our pHs. Okay. The one with the lowest pH should be what? Okay, the weakest or the strongest acid. Okay. What we're looking at is where it changes. So if we think back to that titration curve, okay, we're looking at that pH or that pKa showing up very, very low, which means how much base did you have to add? Small amount or large amount? A very small amount, which means what about the acidity of that bond? Okay, let's go back to that titration curve. Oh my gosh, that's way back there. Okay. If we're looking at a low pKa, okay, to reach that point, how much base did we have to add? A very small amount of base. Okay. If it's a strong acid, what is that acid going to do? Immediately remove the base. So what ends up happening? We end up having to add a lot of base before we see that switch. Okay. In this case, are we adding a lot of base? No. So we're looking at probably the weakest acid. Okay. What does that mean back to the original question? So we need to identify the species. Sorry, this gives you a headache.
Which one's the weakest acid?
Okay, we want to know the weakest acid is going to give us our lowest pH. Because I ran out of space. Let's just do a down arrow. How do we get a weak acid? When do you have a weak acid? What's the opposite of an acid? A base. To get a weak acid, what does that mean about the base strength? The strongest base. So the one that's going to give us our lowest pH is going to be the strongest base. What's the difference between each of these structures? Sterics kind of gets to it. The oxygen is a couple bonds away. It does ultimately contribute, but I would say there's a bigger difference between these before we even get to the oxygen. It's the amount of substitution on our nitrogen. What we're looking at is the ability for the lone pair on that nitrogen to react. Okay. What's going to force those electrons out of the structure? What do electrons run away from? Negative charge. Okay. Which one of these structures has the most electron density around the nitrogen? The one on the right, because it's more substituted. This one is our stronger base and our weaker acid, which means this is going to buffer at a low pH or pH low. Okay. All sorts of flip-flops and inverses on it. Definitely takes a little bit of time to go through and process. Okay. As far as what you would need in a biochemistry situation, would you need to go through all of that? No. What would you end up looking at?
The label.
You'd look at the label where somebody told you what the pKa was, and you say, oh, the pKa doesn't match where I want my pH to be. Okay? Okay. So this is, again, kind of one of those cases where I want you to think about the chemistry behind the label. Okay? Questions about that? Anybody exceedingly pissed at me for this question? Okay, not exceedingly, mildly pissed? Okay, mildly pissed. I can accept that.
Don't have one yet. It's easy.
Okay. Blood buffering. So we're looking at CO2. I'm really only addressing this because it's a question that shows up on the homework, which a good most of you have already finished. The main reason why I want to address it is that when it shows up in the homework, they don't make they make reference to a particular enzyme. That enzyme is carbonic anhydrase. For those of you using the technically current version of the textbook, do they mention carbonic anhydrase in the textbook? I don't think they do. At least I wasn't able to find it. Okay. This is an issue between what Sapling has access to versus what we have access to. They have access to the instructor manual, or not the instructor manual, the next edition of the textbook. And in the next edition, they talk about this reaction in very high detail. The reason why it showed up in the homework is I was able to figure it out without knowing what carbonic anhydrase was. So I figure if I can do it, you can do it, right? Maybe? Okay. So what we're looking at is the blood buffering system, okay? And it's relying a lot on CO2, or carbonic acid. Why would we use carbonic acid, or bicarbonate technically? Bicarbonate has within its ability to make CO2. Okay? Why would that be a helpful thing to have in our bloodstream?
So you can breathe.
Kind of, not, and I would push more to the exhalation. It's a way for us to be able to purge CO2 that builds up in our muscles.
What was the pH?
It will have an effect on the pH, but that's why we're using the buffer to begin with. Okay? And so this buffer has a lot of helpful things with it. First off, it does kind of maintain a pH, but if we tweak the pH slightly, we can start to convert some of that buffer into CO2 that we can now expel. But at the same time, if we tweak the pH the other direction, it ends up taking that CO2 and dumping it into bicarbonate. Okay, why would we want to dump CO2 into bicarbonate? Okay, anybody heard of air bubbles in your blood? Is that a really good thing? No, it's a horrible thing. So if our muscles or general body parts are releasing CO2 gas into our bloodstream, that could be a bit dangerous. Okay, so what our bloodstream has developed is this buffering system where it can now take that CO2 and convert it into an aqueous form. The aqueous form now doesn't have that CO2 gas issue, and we can pump that aqueous form to other parts of our body, i.e. our lungs. And once we get to the lungs, what can happen is we can change the pH. Okay? What would we do with the pH? Increase or decrease the pH in the lungs? Okay? If we decrease the pH, Le Chatelier's principle says what happens? We go this direction, and the CO2 goes where? Into the blood. In the lungs, what do we want? We want the CO2 coming out. So our lung pH could very well be a lower pH, higher acid concentration to help with that removal of the CO2 from our bloodstream. All right? So that whole bicarbonate system is actually kind of cool, okay, if you ask me. That process is also facilitated by carbonic anhydrase, okay, to help push our equilibrium one direction or the other, depending on where we are within the body. Right? So if we looked at muscles, okay, what we're probably going to do is decrease the pH, because what happens? Our muscles are generating CO2. We don't want the CO2 coming out as a gas. So if our if our hydrogen ion concentration decreases and our pH goes up, we shift our equilibrium to form our bicarbonate, and we can convert that CO2 gas into an aqueous format that can pass through the blood and then make it back up to our lungs. Okay? So it's kind of a fascinating process, which is made even more complicated by the inverse of this. What do our blood or what do our muscles need to survive? Oxygen. So not only are we looking at the balance of the CO2 process, but we also have to look at the ability to transfer oxygen from our lungs to our muscles. What transfers that? Myoglobin and hemoglobin. Okay, so we'll end up discussing both of those in chapter 4 when we start looking more at protein structure. Okay, so every once in a while we'll step out from the raw theory and look at the application and then go back to the raw theory. Okay, questions about that? Oh, so if we take a look at that last question, we're going to evaluate carbonic anhydrase. Is it a good idea to use carbonic acid as our buffer system? Probably not, because the carbonic acid that we're using as our buffer is going to change the dynamics of our enzyme. Okay? And we typically want to limit that interaction between the buffer and whatever we're studying. Make sense? Okay.
You're gonna be sad if you don't do a little bit of that today.
You're really going to be that sad. I think we might come back to the mathematics. I do kind of want to move on because I don't know that I'm really going to test you on any of the mathematics applications. I'll be working on building the exam, and if I think I'm going to do the exam with a bunch of mathematics in it, or a question on mathematics, we'll come back and work something like this. Anybody that's taken 152 should be able to go through and do this. It may take a little refreshing to kind of go through and process it, and that's fine.
Is that the ice?
But yeah, we'll end up having to use the ice chart with this. We won't have to go through and deal with quadratics, I believe, because we can get away with the Henderson-Hasselbalch equation, which will simplify a lot of the equations, or calculations too. Okay? So really what I wanted to get into for a little bit at least is chapter 3, looking at our amino acids. Okay, these are ultimately kind of the Lego of proteins. Okay, so our amino acids are the monomer. When we look at our proteins, or technically polypeptides, what we're doing is combining a bunch of amino acids together to build larger structures, or our polymer. Okay, each of those amino acids is connected through a peptide bond, okay, which is the biochemist's way of saying FU to organic chemistry. What is that bond actually? What functional group is that? It's an amide. We're looking at amide functionality. They've decided to call it a peptide bond, ultimately because maybe biochemists decided they didn't understand organic chemistry. Yes, biochemistry. But that's where it ends up getting referred to. Some things to note, which we will keep coming back to, the pKa of your acid portion of that is about 2 on all of your amino acids. And the amino portion of that is about 9. Okay? There are variations between that because one of the things that contributes to those pKa's is what's around those individual functionalities. For instance, what's around it is in this R group. And if we change that R group, that's going to change the acidity of both those functionalities. Okay? So it does see some slight variation. There are all sorts of tables in that chapter that will kind of address some of those variations. I have an activity based on this. Yeah, let's go ahead and just skip to that. We'll come back to all this information later. So